So once again, welcome everybody. Today's class would be on sequential circuit design. Okay, so this is an important class. If you understand things properly here, it will be easy for the next few classes. Okay, today it is going to be the very basic sequential circuit design. Okay, so for any sequential circuit design, right, there are 4 steps, critical steps. Okay, the first step is to derive a state diagram. Okay, state diagram is nothing but since you have many along with the flip-flops and the memory elements. Okay, so there is some state in which the circuit would be stable, so that we call as a state diagram. Okay, slowly we'll understand that for different machines different kinds of state diagrams would be there, different possible conditions, stable conditions of the machine. Okay, or you could even call it as different possible outputs. Okay, different possible outputs at any given time, that could be called as a state diagram. Okay, state table is a table which relates the previous state with the next state. So we'll see that each one of them in detail. Okay, and then from the state table you may make state equations. State equations will help you in implementing the circuit which is required to implement the machine. Okay, and then the final implementation of the circuit. So these are the 4 steps involved in designing any sequential circuit. So we will see that each one of them what it is. Okay, like suppose we got to design a 2-bit synchronous counter. Okay, excuse me, synchronous counter means all the flip-flops will be triggered by a common clock. If it is not triggered by a common clock, then it will be known as asynchronous counter. So we are now trying to design a synchronous counter which will have since it is 2-bit, so at least we will have 2 flip-flops. So both the flip-flops will be driven by the same clock, right? So what is state diagram? Now state diagram is nothing but an representation in a graphical form, the various states or the various states of the flip-flops here. Here we have 2 flip-flops here. So it is 0 0 for the first state, then it will go to 0 1, 1 0 and 1 1. So this is known as the state diagram, right? So this is the state diagram, how this is going to follow here, right? From this state it is going to this state to this state, and it has to return back. So this is the representation of a state diagram. State diagram representation of an 2-bit counter. Okay, what is the state diagram clear?
So if it is for 3-bit, then we have to draw 8, or is it something different?
Yeah, no, this is known as an 2-bit synchronous counter or modulo 4 counter, right? Now I could have a modulo 3 counter. Modulo 3 counter means it will just count 0 1, say it can count 0 0 1 and 1 0, right? So you will require 2 flip-flops, and the state diagram will be 0 0 1 1 0, and it will go back to 0 0, right? And it could be a modulo 5 counter or modulo 6 counter. In that case you will require 3 flip-flops. So in that flip-flops all the states may not be there in the state diagram, right? This machine we are going, in this particular case we are going to use all the 4 states, right? Is it okay?
Yes, sir.
We'll see an example towards the end also, where we will have how do we need, okay, the that will be depending on the states. Okay, n flip-flops will give 2 to the power of n different states. So from the problem statement we need to see how many total different states we require, and we take log 2, then we'll get the number of flip-flops. Is it okay, Swapnil? In this problem we are saying we want a 2-bit synchronous counter, 2 bits, like 2-bit synchronous counter. It is actually mod 4 counter. Like mod 4 counter means it has to read 0 1 2 3 4, so 4 different states. So we require 2 flip-flops. That's how we have zeroed on that it requires 2 flip-flops. So for each problem statement we have to first know, okay, what are the various states. Okay, so the jk value means that we need to satisfy. Okay, so the jk value mean. Jk is the, here there is no jk, right? We are not even speaking about the jk. This can be implemented with D flip-flop or with jk flip-flop. That is a different issue. We will take it on now. This is the just the state machine. This is the output of the two flip-flops. This is 0 0. There are two flip-flops. One full flip-flop will be 0. One will be the other flip-flop will be 0. In this, one flip-flop will be 0. The LSB flip-flop will go 1. So these are the state of the flip-flops. It is not with the JK. It doesn't mean JK. Is it okay?
Okay.
Okay. So now once we know, now from there we need to make the state table. Right? What is the state table is? Like 0 0 is the present state. Next state it has to be 0 1. Right? And if it is a 0 1, the next state will be 1 0. Then if it is 1 0, the next state will be 1 1. And if it is 1 1, the next state will be 0 0. Right? So this is known as the state table. Is it okay? What is the state table? So you need to make all the possible input combinations, and in the next state we'll have to write from this state where it would go here, from this state where it would go. So this is known as the present state. This is known as the next state. Is it okay till here?
So we can directly write the state table, no? So why did we make that state design?
This one, is it? Okay, the previous one.
Yeah.
It is actually preferable once you have a long say English statement. Okay, there are, and this is a small counter. It is a one line statement. If there is a multiple statements, it becomes easy to make an chart kind of thing like this. Okay, if this happens, this goes. If this is not happening, then it goes there. So it is easy to translate the English literature statement into a graphical form first. Okay, since this is a very simple statement, we could have directly made a table. But otherwise, if it is a very big problem, right, if there are 10 states and 10 different conditions, we'll see that once you make sequential detectors and all, we'll see that state diagram is easy to represent a problem statement, and then making a state table will be easy. Okay.
Yes, sir.
Okay. So now we have made a state table. Now from the state table you have to make a circuit. So first we have to decide what kind of flip-flops we are going to use, right? Either we are going to use JK flip-flop, or we are going to use D flip-flop, or a toggle flip-flop. So so let's start with the JK flip-flop, right? So to make with a JK flip-flop, first of all we should know something known as an excitation table of JK flip-flop. Okay. Now what is an excitation table of, let me not show you this early itself. See, 0 0 is going to give QT for a JK, 0 1 is going to give 0, 1 0 is going to give 1, 1 1 is going to give, it is going to toggle the output. Now we are thinking in terms of flip-flops. Okay, now my flip-flop, there are two, one single flip-flop which is available with me, which is at a 0 state. Now in the next clock cycle also I want a 0. So what should be J and K? So that when the present state is 0, when the clock comes, it still has to remain 0. So what should be J?
0 0 0 0.
Yeah. So Vijay said 0 1, Saloni said 0 0, Venkat said 0 0. Ankita says it could be 0 0 or 0 1, right? So all the answers are correct. So let's go with Ankita and say 0 1 or, right, or 0 1. That means I can give 0x, right? Right? I can write it like this. K could be anything. J should be 0, right? By putting an x here, it will simplify it. This becomes a don't care condition. So it will simplify my design. Okay, you will see that, right? So K I am putting it as x, right? Is it clear why it is written X here? All of you? This is very important, right? Once you got, okay. Okay. So now for 0, 1, what should be the J and K values? Anybody? Yeah? Yeah. See, if it has to be 0, 1, right? It can 1, 0 also will give you 1, and 1, 1 also is going to toggle it, right? 1, 1 means it will be toggling it. 1, 0 means it will put it to 1. So in both these conditions, from 0 it will become 1. From 0 to 1, if I give 1, 0 or 1, 1. So I can write here as 1x. So for 1 I will require 1x, for 0 I will require 0x. Okay. For 1 to 0, okay, what is the input I will require? I can give 1, 1, then it will toggle. And similarly, if I give 0, 1 also, it will go to 0, right? So if I see that, so I have to give k equal to 1 and j anything, then it will toggle to 0, right? If I have to keep 1, either I remain same, both the values. So I can give 0, 0, or I can give 1, 0 also. In that case also, it will again slave to 1. So I can write x0. So this is known as the excitation table, right? This is a very, very important table for JK. Okay, as important as this. For a sequential circuit design, you got to remember this table, right? This table is an important thing which you could you explain this table again? Yeah, okay. See, the previous state is 0. Now the next state is going to be 0. So I have to give some values for j and k so that the next state also remains 0. So I can either give 0, 0. If I give j equal to 0, k equal to 0, the same state will continue. So 0 will continue to be 0. Or I could give j equal to 0 and k equal to 1. Here j equal to 0, k equal to 1 is also 0. So I can give 0 and 1 also. So in that case also this will remain 0, right? So instead of taking one particular case, I can put k as equal to don't care and put 0 here. So I'll get 0x. So if you put like this, your simplification in the next stage, it will give me, since it's a don't care condition, I'll get a much simpler gate, right? Is it okay, Swatik, Jangam?
So basically we are just giving the input, like we have the output and we have to determine the input, right?
Yeah.
By seeing the characteristic table.
Correct. This is the previous state, this is the next state. So this table is going to remain, this is a universal table. Now you got to remember this table. This will be applied in all circuits. This is independent of the circuit, right? For all JK flip-flop, this will be the one. Yeah, Aditya, what is the question? If QA and QB do not have identical excitations, obviously they will be different. We'll see that it is going to be different now, because now we are going to use two flip-flops. This is just for one flip-flop, okay, not for the entire circuit. We are telling for each flip-flop, this will be the excitation table. Okay, we can repeat this again. Is everybody clear about what an excitation table is? Because the entire design depends on this excitation table. Anybody has got any doubt in this?
So could you explain the table one more time?
This table? Yeah, sure, no problem. Right? So let me show you one circuit, and then I'll come back here. I'll just flash that circuit so that you know what I am speaking about. So let me just move ahead. Okay, see this is one flip-flop, this is the second flip-flop. So I am giving the clock here, so this has to change to the next output. So what are the inputs which are required to be given to these flip-flops that we are designing here? Okay, so yeah, so we are going to we are taking now one JK flip-flop. Okay, this is nothing to do with the circuit. This is, we are speaking just the JK module. The initial state is 0, 0. When the clock comes, it has to change. Initially 0 here, only single flip-flop. It is going to change we require it to be changed to 0 in the next clock. That means from it, we have to make a transition from 0 to 0. So that means there is no transition required for this particular state, right? Like we are going to, yeah, here from 0 to 0. right? There is no transition happening. So what should be the output there? So what will be the input j and k? So the j could be 0 0 or 0 1, right? If I give 0 0 or 0 1, the output would continue to remain 0. Is this clear?
Yes, sir.
Okay, these are those inputs which we are required to give so that the output remains in 0 0, or it requires to transform from 0 to 1, 1 to 0, or 1 to 1. Okay, so these are the input combinations required, right? So if you see now, if you see this table, okay, let me put this. Yeah, okay, I'll leave it at here. JK. Okay, this is the Q is the MSB, right? LSB 0 0. It has to go into 0 0, then 0 1, 1 0, and 1 1. Okay, these are the present state. This is the next state, which from 0 0. Now let me just consider the case of B, which is the MSB. From here to here, okay, when the counter is moving from 0 to the next state, okay, from 0 0, the next state is 0 1. So 0 is remaining 0. So what should be JB and KB? From the excitation table which we have seen, it will be 0 and X. Is it clear? The first step?
Yes, sir.
Okay. Similarly, in the next state, okay, the Q, which is the MSB, it is from 0 to 1 in the next state. So it becomes 1X. Right? In the next state, the QMSB is from 1 to 1. Right? It is going to from 1 to 1. So 1 0. And in the next state, it is 1 to 0. So it is going to be X1. So this information comes from the excitation table. So you need to know this. You need to, in fact, in exam you need to you may by heart this also, so that it will save time, right? Okay. Similarly, for A also we need an excitation table. So you make 1x, 1x, right? And you put the excitation table for A also, right? Now you have two variables, QA and QB, right? And you have four output variables, JA, KA, KB, JB, JA, KB, KA, right? Now you,
Excuse me, sir.
yeah, tell me.
So how do we get QA T plus 1 and QB T plus 1?
That is from our state diagram.
Okay.
0 0, 0 0 is going to 0 1, 0 1 is going to 1 0, 1 0 is going to 1 1, and 1 1 is going to 0 0. That is from the initial that round state table.
Yes, sir.
From there we got this state table.
Yes, sir. I got it.
Right? Okay. These are the now flip-flops. Now we got to these are the two variables, and these are the four output variables. Now we need to design these four output variables, right? So what is JB? Can you tell me in terms of QA and QB? You can use don't care condition also. Anybody? In terms of QA and QB, what is JB? Right? I think it is because it is not return. No. Our variables are only QA and QB, right? Yeah. Since it is not written in a gray code format, no, you are not able to make a box out here, right? So it is actually QA, right? It is QA. This one. If you make a square here, it will be QA, right? You can club these two into a single map, and it will be QA. Say if you can, if it is 0 0 0 1, 1 0. Actually, it is 1 0 and 1 1. If you write it in an S3 and S2 here, if you swap these two rows, right? You can actually swap these two rows, the entire row. it doesn't matter, then you will be able to map it. So you will get QA for JA. Similarly for KB, I can write the equations. KB also will become QA. JA, if you see, it is all 1. KA is also 1, right? So you got this. Next step is to get the state equations. Anybody has got a doubt in how we got this QA and for JA and KB? All of you have understood how we got QA, and I can repeat this in case if you have an issue. Right? Here, since it is written S1 here and S2, it's not purely written in a gray code manner. So you can club these two, this and this. You can make an between these two rays, you can make a common box in a K map. Sir, can't JB be QA plus QB? So that will be a bigger expression, right? Most simplified expression will be QA. QB is simpler, right? Minimum output, right? So this will be the minimum output. Okay. So once you have done with JN, for the implementation part, okay, you have this, right? So you just need to do this. So you have given the same clock, okay. QA, you have for QA you have JA and KA are both are 1. So this is the LSB. Mind you, MSB is written here in the left hand side. So you have given 1 1, and for A it is QA. So you give the output QA. So now once you give the clock, this will start from 0 0 0 0 1 1 1 2. It will go on reading the desired input. If it is, see, you can see, we can give a test condition. Assume it is 0 0. Okay, if it is 0 0, what happens in the next clock? This is 1 1. This will toggle. Okay, it is 0 here, so it will remain 0 0. So this will not toggle. So the next state will become 1 0. Okay, since this is 1 0 is QA is going to become 1. But if this is an LSB, it will become 0 1. What about the next state? Next state is again this is 1 1. This will toggle. So here it is 1 this time. If it is 1 this time, this will toggle. So it will go to 1. So this will become 1. This will become 0. Right? In the next state, if you see again, if you see that way, this will become 1. So this will count like 0 0 0 1 1 0 and 1 1. Is it okay how this counter works? To all of you.
Sir, I'm a bit confused with QA and QB. Can you repeat this? How did we get this expression?
Okay. QA is the LSB, QB is the MSB. Okay, just remember that. Okay, let me go back. How did we get the expression? Okay. This is the expression, right? So these are the states. For 0 0 I have 0. For 0 1 I have 1. For 1 0 I have X, and 1 1 I have X. Right? So can I make a K map?
So this these two flip-flop inputs we got from the table which was before that.
Yeah.
And this QB and QA values we got from?
Then from 0 0, this is the counter is supposed to go to 0 1.
Okay, yeah.
Next state. Okay?
Yes, I got it.
Got it? This is the next state, right? And these are, to get that next state, this will be the values for J and K, right?
Yes, sir, yes.
And we got to make J and K in terms of QA and QB, right? And then put it here. Is it okay? Yeah.
Yes, sir.
Vijay, you can decide whatever, right? It is, you can write QA here, QB here. So you can write QA, QB here. It will become QA, QB. Accordingly, JA and JB will change. Accordingly, in the circuit also, you will have to put the, here it is shown, it is drawn here, LSB on the left hand side, right? Okay, but it is the LSB and this is the MSB. Okay, so that is a flexible thing. There is no hard and fast rule. You have to name them. Anyone, you can take it anyone, but you have to just see to it that how you are interconnecting. Okay, So it will become clear. We will take more examples. So with examples it will become even clear. Okay, now the same circuit we can also design using the D flip-flops. Okay, so now we need to know the excitation table of the D flip-flop. Okay, so for D flip-flop it is nothing. If it is a 0, you have to give D equal to 0. If it is 1, you have to give D. If you want a 1, you need to give a D1, right? Is this excitation table of D very clear? Unlike JK flip-flop, okay, there is nothing, there is no X. If it is 0, 0, you got to give D 0. From 0 to 0 transmit, you have to give 0. If it is 1, if you require 1 output, you need to give 1. If it is 0, you need to give 0. If it is 1, you need to give 1. It is, you have to give these combinations only. Okay, and that is the reason we prefer JK, because there is no don't care here. For large circuits, it might D flip-flop will not simplify the equation. Yeah, here no, Qt plus 1 does not depend. It is not like that. We are looking at excitation table from a different point of view now. This is the present state, this is the output state which I require, and if I require these outputs, what should be the D value? So this is the D values. Okay, we are looking at from design point of view. Okay, we are not trying to establish any relation between Q and Q plus D. Okay, we are now trying from the designer point of view. Similarly, we have an excitation table for T, right? In the T also the present state is 0. We want to continue it to be 0, then we need to give T equal to 0. If it is a 0 state and if the next state is 1, we should give T equal to 1. And similarly, if it is 1 and a 0, because it is toggle, now we need to give T as a 1. And if it is 1 and 1, we need to give T0, because 0 means it will continue with the same state. So this is the excitation table for a T flip-flop. Is it okay? Is these excitation tables understood by everybody? Is there any doubt in this? No? Okay. So let me move forward. So let's make the table for the same problem with the D flip-flop. Now for the D flip-flop, if you see, right, if it is 0, it will be the same. Okay, whatever is the next value, okay, the D is going to remain same. Now if you see D, in terms of QA and QB, can anyone say what will it be? What will be D? Minimize the expression for D. DB. Anybody?
DB equals
QB XOR QA.
Simplified expression, yeah.
QA XOR QB.
Yeah, it will be QA XOR operation. Similarly, DA.
QA complement.
Yeah, it is QA complement, right? Now you got to express this DA and DB with respect to QA and Q bar, right? You can make a K map also, and if somebody is in doubt, you can make a K map between QA and QB and fill up this data, and you can find out. Okay, so these are the two equations, QA XOR and QA bar, right? So now you how do you implement it? This is a D flip-flop. Okay, this is the LSB, this is the MSB, right? You put an XOR gate and you implement QA and Q bar. Is it okay? How to design and counter using a flip-flop, D flip-flop now? Anybody has got any doubt? No? Okay. So let me go. Now I am going to design a mod excitation table. Okay. Yeah. This is the excitation table for the D flip-flop. Okay. Okay. Now we have to make a modulo 3 synchronous counter, in which you from 0 0 it has to go to 0 1, it has to go to 1 0, and it has to come to 0 0, again back to 0 1 0 1. So for any reason the flip-flop goes to 1 1, say during power up operations and all, okay, it should not happen ki it is continuing in 1 1 or it is making some other path. So you have to define that also. Like if it is in, suppose this is not there in the normal sequence, okay, once it comes into this sequence it will not come, 1 1 will never come, but while switching on the power supply or because of some noise, for some reason if it comes to 1 1, it should come to 0 0. Okay, this is the way we design. Okay, you have to cater for, because it can have 4 states and you cannot be 100% sure that during power off and power on supply it may not be at 1 1, because once you are switching on the power supply, it will, because of some noise, it can go and get stuck at 1 1. So if you don't cater for this 1 1, okay, this counter will not initiate at all. Okay, so this is the state. Anybody has got any doubt about the problem statement here?
Sir, have they given this, or did we create the design?
No, we are not created. This is the problem statement. Somebody says he wants
Okay.
mod 3 means 0 1 3 states. 3 states. Yeah, Shankar, this is the problem statement which is given to us to make a counter 0 1 2. It should count 0 1 2 0 1 2 0 1 2. Okay, the counter should read like that, right? But we are also catering for that 1 1 state, because when you switch on the power supply, it is possible that it might go to 1 1 state. If it goes to 1 1 state, it is possible that it will get stuck at 1 1 itself. It may not come back to this counter itself. So in such circumstances, as a default value, we can always see that whatever is missed out, you can put it to 0 0. You can bring this here also, no problem, right? You can bring this 1 1 to any of the states. Okay, so you make a state diagram. Is it okay? Okay, so we are now just trying to implement small state diagram. Later on we'll see how big problems can be mapped into a state diagram. That we'll see later on, right? This is just a state table which we have got it now. Okay, now if you see, okay, now we are going to use an JK flip-flop. So initially the condition is 0 0. Now I want 0 1. So J is equal to 0, KB is equal to 1, J equal to 1. This is X, 0 1. Okay, this is the next state. It is similar to last time, 1X and X1. Again, then I have put 1 0 here. Okay, here. And for 1 1 I am getting it to 0 0. See, this is the change which has happened here. Okay, for 1 1 I also am getting 0 0, and from 1 0 also I am going to 0 0, right? From 1 0 0 also I am going to 0 0, and from 1 1 also I am going to 0 0, right? So from 1 1 also I am going to 0 0, and 1 0 also I am going to 0 0. So this is the state from the previous 2-bit counter. Okay, this is the change which has happened here. Okay, now you make write all the expressions for J and K. Now you make 4 K maps, QA QB, QA QB, right? QA is the LSB. You are making 4 K maps, and you are deriving the expression for JB. JB 0 0 1 XX. So what is JB? It has come to QA now. Is it clear to anybody how JB has come to QA? Yeah. Is it clear? Okay. Okay. Now KB is XX11, XX11 we have written here. So this can be made into a single K map. So it has become 1. JA. A is the LSB. Remember here, A is the LSB here in this diagram. Here also A is the LSB. So this is also, these are the LSB ones. So you have 1x 0 into 1, xx and 1 1. So it is 1 here, out here. So this comes to Q bar, right? This comes to 1. Is it okay, all these 4 expressions? Anybody has a doubt of how to get these expressions, right? You make a state table, and from there you take all the 4 variables, make a K map and get the equations. Okay, so pretty simple. And now this is the implementation of that. right? You give a clock out here, right? Okay, 1 1, right? Whatever is the expression which we got here, QA here, this is A. JK, it is coming from here, right? From A, this is the LSB, so it is coming from here, QA. LSB is down here, and QB is 1, so you have given 1 here. This is A. This is Q bar B for this. So you have taken Q bar and you have given it here, and then it is 1 out here. So you have, you have given 1 here. So it will.
So there's an So there's an inverter on the clock signal for negative triggering it.
For no, you don't have to bother about the positive edge or negative edge, right? In the negative, that doesn't matter here. In the negative edge, it will just toggle from. See, this state change will happen during the negative edge. That's all, right? For a positive edge or a negative edge, only thing, the transition would happen in the negative edge of the clock. That is the only, like here it is making a transition only in the, since there is a bubble out here, it means it's a negative edge triggered flip-flop. So the transition will make in the graph in the negative edge of the clock, right? It will 0 0 0 1, like 0 1 1 0, and then it is coming back to 0 0. It is not going to 1 1 in this state. It will not go to 1 1 if you try to analyze this circuit. Is it okay with all of you?
Excuse me, sir.
Yeah, tell me.
So, two things. So, first of all, I was a bit unclear with the mod representation. So, we call this circuit mod-3 and the first one mod-2 or mod-4, sir?
Mod-4.
Okay, so that's clear now, because that was 4 states that we were switching between.
Yeah.
And second of all, so we can like make this same, we can replicate the same circuit that we have using 2 SR latches also, right? That would be state triggered instead of edge triggered.
But no, that will create a race around problem. You should not try to make counters with respect. Race around means, see, you have given a clock here. If the data changes right from here to here, that would again give a feedback, change the data. So it will, without even the clock, it will start running off its own. So you should not make, you should always use a flip-flop. You should never use. Either it could be a positive edge triggered flip-flop, or you could make a negative edge triggered flip-flop. Is it clear to everybody? Okay. Now before I go to asynchronous counter, okay, suppose I have say 8 states. Okay, I have a 3-bit counter. Okay, is it necessary that it should go serially like this? Can I have from 0 0 to 0 1 and then to 0 1 and to 1 0 like this? Any random states can it go? Can we design it?
Sir, maybe if only 1 bit is changing, then we can go.
No. Say even for this circuit, let's assume for this circuit, I require first 0 0, then 1 1, then 0 1, then 1 0, then 1 0 1 again, then again 0 0. Okay, can it go like that? Yeah, we can do that, right? In fact, it doesn't impose any restrictions. This is, see, for all these 4 combinations, like these combinations we will write 0 1 0 1 1 0 1 0. This you can write from 0 0, where is what is the next state required? Yeah, it could be 1 0, it could be 1 1, doesn't matter. Understood? Okay, in fact, for your lab assignment, for your lab, I have given a totally random distribution here. Okay, so that you don't have to follow a sequential here. You can have a random thing, and also you need not have all the combinations. So everything is possible. You just have to make the state. First, you have to be clear about what is the transition you require. From that, accordingly, you can make the table. Okay, that need not be one after sequential. Okay, or not. It need not have all the variables, right? You can totally skip this also if it is not there, but that is not a good design. Okay, here it is you should have all the variables here. Suppose it is an 8 variable this thing you are making, and you are making a 5-bit counter. So three of these states will be useless, right? They may not never come, but you should cater for them also actually, and try to put it into one of the variables, so that for any reason the flip-flop is stuck in for any other outputs, it will come into the loop. So not necessarily you should get it into 0 0. Say you have made you have 8 variables and you have made some sequence with 5 numbers. There are 3 left out. So those 3 you can try and bring it into any one of them, or not necessarily all the 3 you should get into 0 0. You can bring, say, one of the variables to 0 0, the next one to 1 0, and the third one to 0 1 also. Okay, from outside. Do you understand what I am saying? Is it confusing, or you understood what I am saying? Okay. So what I will do is, in the next class, I'll give you one more example of a little bigger example, so that the state between the state this thing, and so that things will become even more clear. I'll add one or more examples in that aspect. Okay. Now let's see. So it is very flexible design. You just have to understand the problem statement, make a state table. Once you make a state chart, from the state chart you need to make a state table. From the state table you need to make the state equations, and from the state equations you may need to make the circuit diagram. So these are the 4 steps which we need to follow, right? Okay, this is a mod-5 asynchronous counter. Let me first of all tell you, these are very rarely used, because this has got all the flip-flops are not triggered by the same clock. So this will have a problem. So you have one JK flip-flop here, you have given VDD. So you have given a clock here, and you have taken the output from here and given as a clock to the next state, and again you have taken the output from this state and given to as a clock to the next state. So what would happen? It will run like a counter, right? Will it run like a counter? Because the clock, like initially it was 0 0 0. Suppose it was, actually today I covered it in the tutorials. So the tutorial students will be clear about that. So if you give a clock to a JK flip-flop, with every clock it will toggle. So what will be the frequency out here? If I give 400 hertz, yeah, if I give 400 hertz frequency here, I'll get 200 hertz frequency here, right? So it will toggle slowly, because for every positive edge it will toggle, for the negative edge it will not toggle. Okay, so if you try to make a graph, you will get half. So similarly here you will get half of this. So here you will get half of this. So it will work like a counter. Initially if it is 0 0 0, okay, for the first positive edge of the clock, this will change from 0 to 1, right? Suppose it is a positive edge trigger. Let's assume it's a negative edge trigger, because there is a bubble placed here. So during the first positive edge clock 0 0 0, for positive edge of the clock nothing happens. Negative edge of the clock, this is going to turn to 1. Okay, so the LSB, this is the LSB, so LSB has turned into 1. This is 0 0. Next positive edge of the clock, nothing happens, and next negative edge of the clock, this is from 1, it is going to become 0 now. It is becoming 0 here, right? So you have, this is become from 1 to 0. It is going now from 1 to 0. So that is given as a clock here. So negative edge. So this will now go 1. So it will become 0 1 in the next clock. This is not going to change. In the next positive edge of the clock, right, nothing is going to happen. Negative edge clock, this is going to become 0 to 1. So now you have, right, 1 out here. In the next clock, again it is going to become 1 to 0. That will trigger this to become 0. So that is how this will normally work like a counter. It will slowly, if you make a graph of it, so you will find it is working like a counter. Now if I want a mod 5 counter, that means when I get a 4, okay, I should reset it to 0. So if I take to get a 4, I take a Q from here, right, and I take a Q from here. Okay, it is a mod 5. I think it should have been mod 6. So mod 6 counter means for 5 it should reset, right? Mod 4. mod 5, right? So for the fifth state it should reset. So you take a Q from here, you take a Q from here, you put a NAND gate, and you give a reset to all the flip-flops. So the moment it reaches that value, okay, it will reset it to 0 0 0 0. So it will count only till mod 5. Okay, that is how you design a mod 5 asynchronous counter. If I see the waveform here, if you see the waveform here, okay, the moment it reaches this state, okay, a reset signal will be generated and it will be given. But because of those propagation delays, you will find there are small spikes in the output. Okay, these are the spikes which will come in the output, because this will be first, it will go to that undesirable state. It will go to that undesirable state, and once that undesirable state is, immediately through a NAND gate it will be reset. So you will find that in this graph also, okay, it is 0 1 0 1, 4 states, fifth state is 0, it is going to the sixth state and immediately it is getting a reset here. So you will get this undesirable spike out here. So that is the flaw with an asynchronous counter. So generally we will design with the synchronous counter. Synchronous counters are these counters which we designed earlier, right? So these are asynchronous counters which we generally don't use because of this problem of spikes and noise. Okay, is it okay till here? No, these asynchronous counters will have this disadvantage, right? So that is the reason we go for synchronous. Okay, so you just go through these, some of the textbooks also. There are other examples also. In the next class, for the lab, okay, I have for the next lab, I think lab number 8, I have included the problems like this. I think I have not yet published it. Okay, I'll be publishing it, recording it today, where in this state diagram, it's not a sequential circuit. Okay, like it won't go from 0 to 1 and 1 to 0. Where is the state diagram? Yeah, here for the lab problem. So I have modified this. It will go from 0 0 to 1 0 and to 1 1 and then to 1 1. So accordingly you need to make an combinational sequential circuit for that. Okay, is it okay with all of you? If you have understood everything and if there are no doubts, we'll call it off.
So could you go to the slide for the state table for the mod 3 circuit, mod 3 counters?
Okay. To answer Sapnil's question, yes. State table, this also may not be given. Only some sentence may be given here, right? When we see bigger problem statements, we will have to design this from the problem statement. So this may not be clearly, explicitly be given to you always. The user will only give you this requirement, right? So you'll have to accordingly design. Okay, now you wanted me to go to the state table. Here.
So for the next one with the Q map.
Okay.
The K map.
Yeah, here. Yeah, tell me.
Yeah, alright. So I think I copied mistake. I'll just copy it.
Okay. Anyway, I'll upload this PDF today itself. Just okay.
Alright, so that was
Okay.
Thank you so much.
This video and this thing. Okay. So just go through it. You can get few more examples from your textbooks also. I'll try to put. I have put few examples in the tutorial. So in the tutorial also you'll get a few more examples. One tutorial is dedicated to sequential design. So you'll get I think 5-6 more problems there. So that will become clear. Is it okay? So if it is okay, then we'll stop it here. Okay.
So can you give a brief idea that how can MCQ questions come in this? Like, do we have to fill in the tables or complete?
I told you need to have a paper and pen, right? You might have questions on multiple function optimization, 5-variable K-map optimization and all. So the answers will be there, but you might have to use pen and paper to solve it. Okay, so you can keep it. I'll just see once I have more or less finalized the questions. but I'll see the weightage, because I might not give you all 20 questions. One or two questions which requires more computation will have a slightly higher mark, maybe 2 mark, and the number of questions will be lesser. Okay, it will be simple, it will not be difficult. If you have gone through all the videos, and I am telling you, if you are seeing only the PDF, you might miss out few things, because in the class we do discuss some issues which may not be very clear. If you just see the PDF, you will miss out those points. So I suggest you should go through the videos, and you can probably see it in Chrome. You have that option of running it little bit faster. You can so go through the entire video in a fast mode. Don't miss anything. There will be small hidden knowledge in which will relate, from which the questions have been framed. So you got to be careful with the videos, and please go through my video, my tutorial classes. Okay, I shouldn't be saying so, but then it is possible that some instructor might have missed out something in the tutorial. I might have discussed some few important things in the tutorial also. So most of my tutorial videos are only of 20 minutes, 20 to 25 minutes. So find time, and if you are not in my tutorial session also, just find some time, and just don't rely only on PDF. I am stressing this point over and again, because in we might discuss few things in the which may not be there in the PDF directly, but we would have discussed it in the class. So that questions will be, few questions are framed on those discussions also. Is it okay? Okay, thanks a lot. Then we'll stop it here.
And so in the quiz we have questions from the precautions and safety part as well, right? That we covered in between. Before the QM technique we covered something, right? Is that in the syllabus as well for the quiz?
Yeah, hazards.
Yeah, safety hazards.
Yeah, hazards are there. Hazards are there.
All right. Yes, thank you.
Okay.